Hello, everybody. This is Mr. Steele. I'm here to work through the, as it turns out, last set of video solutions in all of AP Calculus AB and Calculus BC at Franklin High School. It turns out that the optimization problem set slipped through my grasp. I didn't realize that I'd never made video solutions for it, so I'm going to try to rectify that. I'm attempting to work through all 7 problems. I think technically there's 8 because there's one two-parter in here. I'm just going to work through them all. I don't think I'm going to finish it all in one sitting, so you'll probably see me change clothes at some point. My hope for this first session is to record just the first 2 problems. Maybe I'll do a third one. And effectively, like, I am literally just hiding from the Minnesota Vikings being miserably not good against the Eagles right now. So I figure this is a better use of my time, even though you can kind of hear my voice is going, and I've left my water out there so that way I can't stay forever and keep working. So without further ado, I'm going to work through several of the problems on the problem set for optimization. In fact, I'm hoping I'm going to work through all of them. Hopefully the ability to listen to me explain them will add something to whatever you get from the lecture. I think this is one of those topics that having more time to grasp, digest, listen to, and sort of find your way through will actually be of service to you. So that's my hope, at least. So without further ado, let's talk optimization. Without further ado, let's talk optimization now that I can press the button and the page will go forward. So I'm starting with a really basic first problem, although it's got like that weird 7/2. Sure, it's not maybe the best equation in the history of the world to do for this for, but this is sort of, I almost want to call it neutered. I don't think that's the right word, but basically this is like sort of like all of the application-y stuff, all of the real life context is just washed away here. Our job is to figure out a maximum value given 2 different equations. One of these is going to be our objective, at least once we do a little bit of work to it, and one of them is going to be our constraint. So to start with, just kind of reading the problem here, we are told that p is equal to 2x minus y squared. So we don't know what p represents, if anything. It's just here a relationship. But I will note that this is actually an equation that has 3 variables in it. It has the x and y we know and love, but it also features p. It's like a water park in that way. And then over here we have a second equation, which just features y and x. That's helpful information. What that's telling us first and foremost is that our second equation that doesn't feature any of that information is what's known as our constraint. So I'm going to write that right over here. The reason that that's our constraint comes from the fact that y and x are limited by their relationship to one another. In a sense, if you change x, y will necessarily change as well. If you change y, well, x is going to have to go along for the ride too. That is distinct from our objective function, which is going to be the first one we have right there. The p equals 2x minus y squared. The reason why here is that p itself will change depending on what you move x and y to. Both x and y can change independent of one another in that equation, and then p will create its own value as well. So in a sense, like the objective function is we're going to be work to find the maximum value of. So maybe it's also worth pointing out that, hey, it tells you want to find the maximum value of p. That means that this is where the objective function is going to come from. As soon as we're asked for the max or min of something, that's going to provide our objective. So given this information, the question then becomes, what is it that we do from here? How is it that we find the maximum value of p? Like, because in a sense, in your mind, you're like, well, shoot, there's x's and y's both in there. How do we do that? Well, we're going to treat it just like anything else that we try to optimize, aka find the absolute extreme of 4. We are going to use the derivative. Before we get there, though, we need this relationship to be in terms of just one variable because we haven't learned implicit differentiation yet. That's a weird kind of Franklin thing, although you wouldn't use that in this technique anyway. In a sense, what we need is something that allows us to differentiate with respect to just one variable. And typically, I'm going to try to be a heat-seeking missile trying to find x and make x our one thing. So in this case, that's what I'm going to do. I'm going to start with the constraint. That is true in going to go ahead and say pretty much every optimization problem. Start with the piece that provides you a concrete relationship between 2 variables. So in our case, if y equals 2x minus 7/2, well, actually it's already did the work for us. We already have y by its lonesome. What that allows us to do then is substitute it into 2x minus y squared. So I'm going to take that objective function, p, which is equal to 2x minus y squared, and I'm going to go ahead and substitute in 2x minus 7/2. So this might feel weird itself, but all I'm doing is using substitution. I'm just going ahead and replacing that value for y, so that way we have p as an explicit function of x. as in there's only one variable over on the right side, and it happens to be our classic independent variable. So from here, I've got a little bit of algebra to do. I will admit that you could just use the chain rule to do this, but I feel like that's going to throw people off a little bit, so I'm going to be extra careful here. So what does this multiply out to? Well, that's going to be, if I use the imagine multiplying out the binomials of 2x minus 7 over 2 times 2x minus 7 over 2. Again, I'm saying imagine, and I'm writing it out. That's because I'm performing for you right now. This is going to be 4x squared minus 7x minus 7x. And I'm just going to go ahead and assume that you're okay if I just rewrite that as 14x. And then finally plus 49 over 4. Now that is what is being subtracted here. So actually I'll use the correct pen colors. Oh, come on. I'll use the correct pen colors. Sorry, I'm recording a video solution set in OBS for the first time. I'm also using this as sort of an experiment of sorts. Now with that in place, we're going to do 2x minus that whole thing. Using the x squareds first, we're going to have minus 4x squared. Then we'll have 2x minus a negative 14x, which will be plus 16x. And finally, we'll have minus 49 over 4, which will just be minus 49 over 4. There was no other constant to combine with. And this entire relationship is p, which actually is pretty close to what I had a few seconds ago when I messed up, but go figure. So what do we do with this? Well, we're trying to find the maximum value of p. And if you want to find the maximum value of something, the candidates include endpoints and critical numbers. And in this case, we're not provided endpoints, so the assumption has to be that we're going to find that at a critical number. So let's find critical numbers. Let's take the derivative of p with respect to x, and then set that derivative equal to 0. And since this is quadratic, something you've probably already realized, that the derivative of a quadratic function is linear. It'll be clean and easy for us to solve. So looking at our relationship here, p prime of x is going to be equal to negative x plus 16. If we set that equal to 0, I'm hoping you two can notice that this is equal to 2. So x equals 2. So in a sense, like that's huge. Like, it's not the answer to our question here, not specifically. What we found is there is one critical number here. There's only one potential candidate. And I'll call it a candidate, even though we don't have endpoints. We're not explicitly doing the candidates test. There's only one candidate here for us to potentially use. So now, before I go forward though, and before I plug it in and check it and try to make sure it's the correct value, I need to actually make sure that it is a maximum. So to do that, like in order to make sure it really is a high point here, a relative high point, or a high point in any way, and I think it will be, is I'm going to go ahead and use the first derivative test. Now having said that, if you're looking at this relationship and going, it's a negative quadratic, it's a frowning parabola, it's okay. Yeah, but I'm trying to show it with calculus. My goal here is to demonstrate good calculus. So I'm going to go ahead and set up my little sign chart. It doesn't have to be over fancy. I prefer to have the little column in the center where the slope is 0. Put little p prime over on the side. Then I'm going to have x less than 2 and x greater than 2. Now, as you know, when we go to check this, we pick a value that's in each interval. I'm going to choose 0 and 10. It's just my personal choice. You can choose 3 if you want. If I plug in 0 to our first derivative, 0 plus 16 is positive 16. And if we plug in 10 to the other one, we're going to have negative 80 plus 16, which is negative. So based on this, based on what we just saw, our derivative changes from positive to negative at x equals 2. Well, as that indicates, since our graph is now going from increasing to decreasing, that means we have a local maximum. So what I'll put underneath here is, therefore, we have a local max. And really the important part here is that it is a maximum. It's a local max at x equals 2. So that's good. We have just verified that this is, in fact, sufficient. I guess if you wanted to say it's a local max at x equals 2 because p prime of x changes, like we could do the entire first derivative test statement here if we so desire. It changes from positive to negative. But in this case, like I've often seen the justification on optimization to just consist of drawing the sign chart. But, you know, sort of follow the procedures, check the written solution, see where you go. Now, once again, we're at a point where it feels like we're done. It feels like we've done the trick, we've got everything in place here, but unfortunately we don't. The reason we don't is that we were asked what the maximum value of p is. That is asking us what is the largest y value that we get here. And in order for us to find that largest y value, we need to plug our x value back into the original function. So what I'm going to do is I'm going to plug it in all the way up here. And again, I don't have to. I could technically plug it in right here as well. But I'm going to go all the way back to the beginning just because I want to make sure that I have the key relationship in this case. So I'm going to take that x equals 2. I'm going to calculate that p is equal to 2x. Sorry, that'll be a 2 in there. Minus the quantity, 2 times that x, minus 7 over 2 squared. From here, I'm going to go ahead and plug in the value of x equals 2. When I do, I'm going to get that the value of this expression p is equal to 4 minus, over here we have 4 minus 7 over 2. That's 8 over 2 minus 7 over 2 is 1/2. And of course, that's being squared. Again, if you don't see that, 2 times 2 is 4, and 4 becomes 8 over 2. Therefore, 8 over 2 minus 7 over 2 is 1/2. And if I clean this up a little bit, I'm going to get 4 minus 1 over 4, which is going to be 16 over 4. Notice how often the recomposing things as fractions helps. This will be 16 minus 1 is 15 over 4, I'm seeing. So it looks like the maximum value of p, I'm going to put p max, looks like it's equal to 15 over 4. And I should say the p max value, it is the value, we're just looking for the y value in this case. There is our stuff. And interestingly enough, we've actually done all of the work that was necessary here. We did complete analysis. We went through, we computed the derivative, set it equal to 0. By the way, the reason I didn't check where the derivative was undefined was because this is a polynomial. At least once we've substituted it in. So polynomials are differentiable and therefore continuous everywhere. And then from there, we went through, we did some quick analysis to justify that we had a maximum. And then last but not least, we actually found that maximum by plugging the x value in to get the corresponding y value. So sort of nice. I think this feels really complicated because there's a lot of stuff going on and I'm having to say a lot of jargon as we talk, lots of rich vocabulary. But keep in mind, my goal here is not to work through the problem authentically. My goal is to help you sort of make peace with what's happening, to give yourself a chance to let it soak in a little bit. Give yourself a chance to have a tool where you can rewind back a little bit and hear me say it again. To rewind back a little and hear me say it again. To rewind back a little and hear me say it again. Just like that. So yes, we're about to switch to the second problem. I just have to say that if you're noticing the literal light is changed, the closer changed, everything is changed, that's because when I attempted to finish this video several days ago, and by finish I mean just get to the second problem, I actually fell asleep standing up while doing it, so I'm back to try one more time. So here we go again. Here we go again once I press the button. So the second problem that we're going to attack is yet another optimization problem, and my goal is to just kind of go through the entire collection here as much as possible. And in this case, we've got sort of a classic setup. We've got some information about two different numbers. I think this time it's information about their sum, and we want to maximize some other relationship that involves them. In this particular case, though, there's some extra information here. So first, let me just kind of read the problem to get us into it. So it says, consider the numbers x and y. By the way, it says numbers. It doesn't say integers, so for what that's worth. Whose sum is 9, and let p equal x squared over y. Now that's already a huge piece of information that they're giving us here, so I want to dive into the information that they gave us. The first thing that I note is that they say that the sum of these two numbers, x and y, well, something just happened there. Okay. Says that the sum of those two numbers, x and y, is 9. Now, interestingly enough, normally I try to find my objective function first, but in this case, they're telling us these two numbers have to add up to 9, and that's limiting what numbers we can possibly choose. We can't choose 10,000 and negative 38 because those don't sum up to 9. So that's going to be our constraint right off the bat. X plus y has to equal 9. Likewise, as soon as we establish that, we can see that we're trying to eventually find the minimum value of p. But you could also just kind of infer that that's going to be the objective function, the thing we're trying to maximize or minimize, because it's sort of provided as a function of both x and y. So there we go. We already have our two pieces. So from here, though, we've got some extra information that we're going to want to work with, because in this particular problem, we're told that we're only going to be considering x values between negative 3 and 10. And that's also going to constrain us a little bit. In fact, you could also theoretically throw that down here as sort of a second piece of information that contributes to the constraint. But more important than that, I want to point out that since we're on a closed interval like that, that means that we're going to actually have to use the candidates test. Basically, candidate's test is what's going to find the absolute extrema on a closed interval. In this case, we're only interested in the global minimum value on this interval, but at the same time, it's still the candidate's test. We're going to have to look at both critical numbers and endpoints in order to find where this where this minimum value is actually going to occur. So with that said, basically, let's get into the problem and try to figure out where that goes. So we've done this before. Like, our first thing is we need to find some way to combine the objective and constraint equations together into a single one. And that's almost always going to begin with the constraint equation. If x plus y equals 9, then it's not asking too much for you to just subtract x from both sides and get y equals 9 minus x. That way we have what we're going to call an explicit relationship. Y is a function of x, and that's going to allow us to plug into our objective function so that it goes from having 3 variables down to 2. So in this case, we have p equals x squared times y. That is going to be transformed into p being equal to x squared times y, and we are going to wisely put 9 minus x into our equation. Now from here I could stop and just call it a day right there, but I'm going to take it one step further here and write this as 9x squared minus x cubed. That's just kind of speculative, but I know differentiation is a big part of these problems, so I just wanted to have that ready. So in a sense, this provides us our new version of the objective function that sort of has the constraint baked into it. It's like both those relationships are now conveyed in this single relationship. But now that we have p as a function of x in a sense, and I guess I could even call it that, now that we have this, we need to compute its derivative and set it equal to 0, because at this point we're trying to maximize on that closed interval p equals 9x squared minus x cubed. So that's going to be my next move. What is p prime of x? And that's going to be as a conduit to us finding our critical numbers. So fortunately, this one's not difficult to compute the derivative of. That's going to be 18x minus 3x squared. If I factor out some GCF stuff, I'm going to pull out negative 3x. That's going to leave me with x minus 6. I'm going to do a quick little distribute in my head to make sure I did that right. Minus 3x squared minus a negative 18x. Good stuff. And when we set this equal to 0, that's going to give us two separate critical numbers. It's going to give us x equals 0 and x equals 6. Now those aren't the only candidates, but those are both candidates. The absolute minimum on this interval could occur at either one of those values. Well, we also, of course, need to consider the endpoints, but the endpoints aren't hard to find. I mean, if you want to even list them down just so you can feel like they're there, the endpoints are established by the interval they gave us. They're going to be x equals negative 3 and 10. So with this in mind, I'm going to go ahead and set up the candidates test. And again, candidates test because we're on a closed interval. We're using and seeking the global maximum, or excuse me, global minimum on this interval. Really want to maximize everything, can you tell? And basically, I'm going to set up my little candidates test table here. I love that I'm doing this at home and not on the board at school, where everything is unfortunately like too low for people to see well. I don't have to stress about that here. So for endpoints, I got negative 3 and I got 10. And then I've got those two critical numbers of 0 and 6. And now to be fair, off the top of my head, I don't actually have like a great picture of what's going to happen here. I know that that negative noodle is going to look something like that, but I just don't have a good sense of where everything is. I'm sure I could if I wanted to. I'm just going to try to trust in the process here. And as a reminder, we're going to plug back into our original function. Remember, we're trying to find the minimum value of that function, so it only makes sense that we plug it back into the original. Where is my original? It's right up there. It's 9x squared minus x cubed. So we're going to first plug in negative 3. So that's going to be 9 times 9 minus a negative 27. That's 81 plus 27, which is 108. So nice value to start things off. Plugging in 0 is the fun one out of the bunch. It's going to be 0 minus 0 equals 0. So right now 0 looks like our minimum, but we do have two more values to check. Next, when I plug in 6, I can tell this one's going to be a little bit crunchy, but we'll make do. It's going to be 9 times 36 minus 6 cubed. Now I happen to know that 6 cubed is 216. So the question is, what is 9 times 36? Well, doing this one piece at a time, 9 times 30 is 270. 9 times 6 is 54. The important thing for me to note here is that 1, yeah, I could show that this is equal to 108, but I don't really have to. The important thing is this is larger than 0, so it's not going to be the absolute minimum. So I'm going to stop calculating it right now just to save myself the arithmetic trouble. The arithmetic trouble? The arithmetic trouble, however you want to say it. Last but not least, if I plug in 10, that's going to give me 9 times 100 is 100. minus 1,000, and oh, that's actually pretty big here. 900 minus 1,000 is negative 100. And by the way, when I said that's pretty big, I mean like it's big for us. It's going to open up this problem because this is our smallest value. In fact, I would say this is our minimum, which is great. So now that we have this as our minimum value, we can finish our problem off. We've identified the smallest. Therefore, we can say that the minimum value is, and I'll just put it in the original color, negative 100. So that gives us our value. Now, as a heads up, you'll notice that this problem doesn't ask you to justify your answer. In truth, it could ask us to justify our answer, but we wouldn't have to do anything else to do that. In fact, I almost feel like I should go back and add that instruction just to point out that the candidates test is justification. By finding clearly, and of course with well-labeled and organized work, by finding the two critical numbers and then comparing the y values at those critical numbers as well as the candidates test, we have justified that the minimum value is negative 100. So the candidates test is its own justification, or justifies the existence of a global extrema. The only thing we could have done here just to make sure is we could have guaranteed or stated a guarantee that the function was continuous in question, so that way this application of the extreme value theorem would be 100% valid and sort of unimpeachable. But I'm not going to bother. I feel good about what we have here. We've effectively found it. And if I click on some stuff, yep, there it is. It does match the solution that I got in the written solution. So that's a good thing. Granted, I have to go correct this a bunch because I made a couple of mistakes as I was filming it. But that's okay. Valuable lesson for all of us. The third problem we're going to hit has a little bit of decoration to it. We brought the old McDonald how to farm EIEIO thing into it. But for the most part, this is kind of a classic optimization problem. It's simple enough that even without calculus, you can usually solve it. But we are, of course, going to use calculus because that's the purpose here, is we're trying to demonstrate the use of calculus to solve optimization or applied min-max problems. So we're talking in this case about this guy, Old McDonald. He has a farm. He bought it on eBay. Good for him. You can tell I wrote this problem. At his farm, he wants to build a rectangular pen with 6 parallel partitions. So I'll do this in silo or barn red here. That will divide the pen into 7 separate rectangular lanes. I think you can also tell that I wrote this problem set really, really late in the game. He's going to race turtles. Yeah, you can tell I was just being goofy. But in any event, okay, so first of all, we need to construct an image of what this looks like. I think it's kind of complicated until we do, so let's do this. 6 parallel partitions that will divide the pen into 7 separate rectangular lanes. So first of all, let me do exactly that. 1, 2, 3, 4, 5, 6, 7. So I'm doing this way so we can kind of make 7 partitions here. I don't know if this is going to be the best drawing in the history of the world, but hopefully it does the trick. There's 1, 2, 3, 4, 5, 6. Okay, so there it is. It looks like one of those, like, what are they called? An old washboard. But in any event, this is the pen that Old McDonald's been doing. So you can imagine he's got his little turtles in here. Let's make sure I draw my nice little turtle. Turtle! Looks just like my armadillo. Yes, it does. Don't you dare judge me for that. Turtle. Teenage Mutant Ninja Turtles. Teenage Mutant Ninja Turtles. Turtles in a half shell. Turtle power. Okay, there we go. So there's our turtle. You can imagine this little turtle guy going to be racing inside there. Turned into a lump. Okay, close enough. Whatever. So in our little parallel partition here, basically, like I want to give some names to these things. I want to describe them as best I can because we're talking about building these rectangles and having fencing and all this stuff in this problem. So what I'm going to do is I'm just going to choose to call this 2 different variables. I'm going to use lengths and widths as we usually would for rectangles. I'm going to call this width. Like, yes, I peeked at my solutions to see which way I oriented these variables just for simplicity here. So I'm going to call each of those a width. Now again, that includes the 6 parallel partitions in the middle of the rectangular pen as well as the 2 outside ones that are bounding the outside. And then I'm going to call these outer portions L. If you wanted to instead say that there are 7 L's in there, you could. I just think it's probably easier just to kind of point out that those are there. I think this is probably the straightest forward way to do it. So there's our situation. He's racing turtles in there, blah, blah, blah. Built a rectangular pen using 320 feet of fencing. So basically, he's got only 320 feet of fencing to make this turtle pen out of. I'll use that color since I use green for the turtle. And we want to figure out the largest pen. We want the largest rectangular pen in square feet. So lots of information here to interpret, but the situation is really helped by the fact that it's rectangular. Rectangles are pretty easy to work with. They create linear, or as we'll see, quadratic relationships out of them just because of the nature of the variables. So, okay. Why is Camtasia doing that? There we go. So first of all, we've got this piece of information about 320 feet of fencing. Best thing to start with is probably right there to interpret what is that telling us. Well, if you only have 320 feet of fencing, you can't make this partition, you can't make this pen 7,000 by 96,000 because you don't have enough fencing. That is to say, that is your constraint. Somehow 320 is going to be involved in this. And then from there, to decide what 320 is equal to, we can think about what comprises that 320 feet of fencing. Like, where is it going to go in Old MacDonald's farm rectangular pen house thing? So in looking in here, basically that's going to include all of the outside, plus it's going to include each one of these little partitions on the inside. And the reason I'm marking it up there is just for you to see where it is that this equation is going to come from. As we put all this together, you can tell that that fencing is going to require 2 lengths worth, basically this side and this side. And then it's going to require 1, 2, 3, 4, 5, 6, 7, 8 of the widths. That's because there are 8 pieces, 2 on the outside and then the 6th in the middle to break it up into 7 sections. That means we're going to get 320 equals 2L plus 8W. And now you don't have to do this, you can keep it this way, but I noticed that all 3 of those terms are even or have even coefficients, so I'm just going to go ahead and clean that up a little bit and make it 160 equals L plus 4W. My thinking is that's just going to make our computations a little bit easier. And anytime I can make that a little easier, since this is a no calculator problem, I should probably take advantage of that, you know? Now from here for the objective function, we want the largest pen in square feet. And I would say right there, the fact that we want it in square feet tells us that our objective function is going to be an area. We want the largest area pen. And if we look over at our picture here, what is the area of that pen? Well, it's pretty obviously length times width. Because the way we named the portions, the boundaries of the pen, it is just classically L times W. So that's not going to be too complicated for us to work on. Now, of course, we do want to maximize that area, but that's something we'll check with at the very end. Now that we've got our objective and constraint, the next portion of this problem is literally just a bunch of algebra and then calculus. So let's start there. So we have A equals L times W, and we have this other relationship, 160 equals L plus 4W. Well, I'm going to go ahead and do the easy thing, because why not? And I'm going to solve for L. Like, I'm going to take the L and leave it by itself. We're going to get 160 minus 4W equals L, and then I'm going to take the L and plug it into our original area function. This is going to give us the area equals that L times W, and that L was 160 minus 4W. From here, I'll go ahead and distribute everything in, just to kind of get it there. And we're going to end up with A of W. A and W makes me think of the root beer. But beside the fact, we'll have 160W minus 4W squared. So there's our relationship. In a sense, this is the equation that combines both the objective and the constraint functions. That's always what we're seeking, which is great. And now that we have it, we can, of course, do the calculus portion. Our job now is to figure out, well, what's the derivative? Because in a sense, what we want are the critical numbers. Those are the places where the max, in this case, could actually occur. So I'm going to go ahead and do exactly that. Change the colors here. So A prime, I'm just going to call it A prime. I'm going to drop the W. Hopefully that's okay. Drop the W, but I took the L. It's not been a good day victory-wise. So the derivative here is going to be 160. By the way, again, we're differentiating with respect to W, so this makes sense. 160 minus 8W, and we want critical numbers. And this equation is almost trivial. I'm going to go ahead and trust that you can get W equals 20 from here really, really quickly. So cool. We've got W equals 20. This suggests that the largest pen will occur when W equals 20. But we don't actually know that that's the maximum. Like, theoretically, that could be a minimum. Now, I know you can make the argument that this is a negative quadratic, and yeah, of course that's true. But like I said, I'm trying to demonstrate really good calculus here as you're watching this video. That's my goal, is to make this so it's as comprehensive and as meaningful in calculus terms as possible. Not necessarily the fastest possible solution to the problem. So in that case, I want to do some good calculus here. What I want to do is, I've done the second derivative test before. I think I did that on the first problem. I'm not going to do that here. I'm going to use the first derivative test here. So what I'm going to do is I'm going to set up a sign chart, and I'm going to analyze the sign of a prime of w relative to some values of L. Now in here we've got our critical number, which by the way we just stated was going to produce a derivative of 0. But we've got those other intervals to consider as well. Now technically you could just say w is less than 20, but I discourage you from doing that only because w is the width of a pen, and what does negative 17 width mean? Like it folded in on itself? Is that some sort of wrinkle in time thing? I don't know. I'm just going to go ahead and include the 0 there. It's not something that you'd be marked wrong for. I'm just trying to be as accurate and realistic as possible. And then on the next one, there's also limitations, I imagine, on what the width could be, because of course we can't go forever. Like there's a whole bunch of them here, and you can't just have this tiny little thin thing. But I'm just going to treat our sign chart as being important around the actual critical number. So with that said, next what I want to do is I want to go ahead and test some values here. So I'm going to pick values that are easy to plug in. I'm going to plug in 10 here, and I'm going to plug in 30 here. I feel like those will be pretty clean. I guess we'll find out. If I plug those in to our derivative, which by the way, that derivative is right here, there's a prime, that's going to give me, first of all, 160 minus 80, which is 80, otherwise known as positive. And if I plug in 30, that's going to give me 160 minus 240, which is clearly negative. Based on that, we just showed that a prime changes from negative to positive. Oh, sorry, changes from positive to negative, excuse me. From positive to negative at w equals 20. And of course, based on that information, therefore, a has a maximum. And we could say relative maximum, but we're just going to go with maximum here. Has a maximum at w equals 20. And that's important. We have now verified, in fact, that we have a maximum. It's the only critical number, so that's important. And of course, we didn't establish a finite interval, so we don't have to do the candidates test. All that means, though, is we're now eligible to kind of finish this problem and state what our answer is. So keep in mind, our question was what was the largest pen? So we can't just say w equals 20 and be done with this problem. We need to actually find what that largest pen would be, which is when w equals 20. So let's make a quick little note here. If w equals 20, then we know 160 minus L, or equals L plus 4 times 20. And based on that, 160 equals L plus 80. That's going to give us L equals 80. So we have W equals 20 and L equals 80. The last thing we have to do then is come back up to our pen, and I'll use turtle green for this one. So A is equal to LW, so the maximum area, I'm just putting a little subscript of max in there to make it clear what this is. That is going to be equal to L, which was 80, times W, which was 20, and that is going to be 1600. Now I should include feet. I mean, I guess they told us square feet, so this will be in square feet. But this is the largest area that that pen can include. Which, you know, I don't know much about turtle, like, movement habits or what, but I feel like that's a good amount of space. I feel like that's great real estate for them, right? Right? I mean, it's got to be pretty good, right? They've got like 1,600 square feet. They're turtles, right? I mean, if they're Ninja Turtles, they'd live in the sewer, so it should be fine. So sorry to let the dialogue splinter off right there. My bad. Can I think of a way to get Shredder in? No, I can't. There's problem number 3. The next problem we're going to attack is question number 5. I am purposely omitting question 4. I think the written solutions do an excellent job of walking you through it. And the written solutions even include the kind of cool alternate approach that uses perpendicular lines. So I'm going to leave that completely to you. If you want to learn that, you can, but that's not going to be something that I'm going to plan to include on the test anytime soon. It's too calculator-y. There's lots of ways to kind of break the problem if you have a calculator. So instead, I'm going to focus on problems that are more realistic, that I could potentially ask you on a test. One such problem is question number 5, which calls back to, in Accelerated at least we did it, I think they did it in Honors Pre-Cal as well, some of the work that you did with sort of open top boxes. It's not exactly that problem, although theoretically that question could be asked in some way too. It just doesn't appear on here. I have some kind of new favorites to throw in there, but it's related to a box, basically. We're trying to maximize the dimensions of box or minimize the dimensions of the box. I think part B is minimized. We'll see when we get there. So in our situation here, though, we've got a rectangular box. It's going to be designed with a square base with side length w, inches, and a height of h equals 15 minus 2w. So just right off the bat, that's a lot of information to throw out there. So basically trying to grab onto all of this, we have a rectangular box. It has a square base. It has side length w in inches, by the way. I guess we should note this is in inches too. I guess I'll mark that. It has a height of that, and it's also in inches. So basically they've given us a ton of information here. So just based on that, I'm going to try to draw out a box just so that I have a decent visual of what's happening here. And again, I learned how to draw boxes in 3rd grade, so I'm super proud of my box drawing skills. Shout out to Folks Ranch Elementary School. I think it was after school in Gate, or maybe after school in some art class that taught me how to draw my boxes. Now, in fact, they actually taught me to draw this little, what is it called, these invisible lines or whatever, so that way I could see both sides. I'm not going to bother with that here. Instead, I'm going to focus on what we have. So since this is the base, that's going to be w by w. And then we have our height, which we can mark as, 15 minus 2w. So really valuable stuff to know. Especially because we're interested in the largest volume that such a box can hold. So right off the bat, we actually can kind of see where we're going. We want the largest volume. That is code for the objective function. It's what we're trying to maximize. So over here in my objective function, I'm going to put in there, we want the volume. And to be fair, volume for a box, a rectangular box, is length times width times height. And in our case, I'm hoping you can see that that volume is going to be width times width, so width squared times height. Now, if you're asking why I didn't just plug in 15 minus 2w, it's actually sort of contrived. It's because we need our constraint, and our constraint is actually this guy. It's literally that the height is stuck being dependent on w. So like I said, this is a little bit contrived. I'm not sure why that would have to be, although there is a problem that I've run into in the past that talks about the formal measurement of what's called girth in a package in the post office. So basically maybe this is related to that. But for us, we'll go ahead and say that that's our constraint, 15 minus 2w. And note, by the way, that that does put some restrictions on the value of w we can choose. I haven't made a big deal out of this, but you could also point out that w has to be between 0 and 7.5, because that would otherwise make the height 0 or 0. Basically, you've got to stay in that window to make this work, but I'm not as concerned about this particular thing myself. It's just not my focus at this point. I'm trying to get you comfortable with the big problem. I would hope that if you plugged in a value for the width and saw that it gave you a negative volume, that you knew something went wrong. But so we are. Okay, now, we're supposed to bring all this information together into a singular equation. And of course, I think you can anticipate this. We're going to plug h in right over there, in for h, just like you'd expect, and just like we've done a few times. V is going to be w squared times h. As we said before, our h is 15 minus 2w. And I'm going to go ahead and distribute in w squared. We're going to get v as a function of w as 15w squared minus 2w cubed. And this is our objective function as a function of just a single variable, which allows us to start getting into the calculus part of this problem. We're now going to differentiate and then set equal to 0 to find critical numbers, and then we'll check whether they're maxes or mins to hopefully find the exact value that we're going for. And as a heads up, it helps certainly that we don't have a closed interval here. Obviously, we know that there's some restrictions built in, but because there's no closed interval, it would appear that the max that we potentially find, or any max we'll potentially find, is probably going to be the correct one. So let's get into the problem and find out if that's true. So in looking here, I'm going to go ahead and use one of my favorite colors. Basically, I want to compute v prime. V prime is going to be 30w minus 6w squared. And if I factor this out, I'm going to get negative 6w times w minus 5. And of course, if we set that equal to 0 in our search for critical numbers, we're going to see that w is either equal to 0 or 5. But we already established that w really can't be 0, because if w is 0, this box wouldn't be a box at all. It would be a terrible box. No, it just wouldn't be a box. It'd just be a flat piece of paper, which does not work in our case. So in this case, we know it can't be 0. That leaves us only one critical number, which is pretty awesome. So basically for us, the only candidate that we have here for this maximum volume is going to occur when w equals 5. Well, With that said, we should probably still make sure, right? I mean, that's part of the whole thing, is we should justify our answer. I know that this problem doesn't specifically ask us to find it, but I'd be much more comfortable if we did. So let's see, what did I do last time? I think I did the first derivative test on the last one, so let's do the second derivative test. So v double prime is going to be 30 minus 12w, and we want to go ahead and check what happens at, 5. So we're plugging in that value from before. So what is this value? Well, this will be 30 minus 12 times 5, which is 60, which equals negative 30. Now, negative 30 is less than 0. Pretty obviously, it has that negative in there, which means that our function v is concave down. And even though I know what this means and I know what this statement comes from, I often, when I get to that point, I just kind of draw a quick little thing and go, oh, yeah, that's right. Concave down would be a relative maximum, just because it's sort of counterintuitive. Down makes big, maximum. Up makes small, minimum. So just drawing the picture, I think, helps a little bit. What this tells us is that there is a maximum at w equals 5, which is good. That's what we wanted. We were hoping for that. So that's really a good thing. All that it leaves us with then at the very end is actually to find that largest volume. Like, well, what is it? Well, if w equals 5, then we can plug that into our original volume equation, which is going to be, as we saw it there, 15w squared minus 2w cubed. And I'm going to go ahead and just make that substitution. I'll put 5 in for each of those. And actually, I'll use the color just to make it a little bit clearer. Put 5 in for each of those. As I go to evaluate this volume, that's going to be 15 times 25. Not sure I'm hugely a fan of that. Minus 2 times 125. But that's okay, I can do this in my head. 10 times 25 is 250. Plus 5 times 25 is 125. Minus 2 times 125. Well, look at that. We got 125 minus 2 times 125. That's going to be 250. Oops. Yeah. It's still going so well. 250. Come on. Minus 125, which is 125. And then as far as units, like, it doesn't ask us to include units. On the AP exam, it would always say include units if they want you to include units, and they're going to hold you to it. But in this case, since we have it, we were talking volume, we got 125 inches cubed, which is good stuff. Awesome stuff. So there is our maximum volume. That's the biggest space that our box can hold, which is great to have that information. And in this case, we use the second derivative test to go through. Maybe I should make a quick little note of that. We did the second derivative test to get through here. Again, you don't need to cite it by name. You just need to include all the stuff. But since these are instructive videos, we'll go through. And pulling this up a little bit. Oops. There it is, pulling it up. The correct solution is 125 inches cubed. Good stuff. We did that one correctly. Good job, us. Pat on the back. Now, there's a second part to this question. Like, you can see it. It's part 5b. And this one asks us what the smallest surface area for such a box can be if we're given the restriction that w has to fall between 1 and 7. And I'm definitely a big fan of this one because it involves the candidates test again. When I rewrote this problem set, I was really trying to get some candidates test stuff in there. That's basically a nod to one of my professors at UC Davis, Dwayne Kuba, who was big on the applied min-max problems and almost always involved some checking of the endpoints in there, from what I recall. Or I didn't take him for this class in particular, but I saw from his website that he always did that. He's an amazing professor. If you go there, he may still be there. Really, really good guy. And really good teacher. Really good teacher. So from here, basically, oops, I broke my box. Come on, box. Stay. Stay with us, box. You can do it. I think that we'll make it after all. Okay, so there's our box. Same box as before. This second question is talking about surface area. And I'm going to point out right off the bat that some people might not actually remember formulas for surface area. So I do want to point out, though, that this is asking for the smallest surface area, which means whatever our surface area equation is, it's going to be the objective function. We're going to be trying to make it as small as possible. And then as far as constraints, well, this is sort of silly, but our constraint is the same as it was before. We still are constrained by having h equal 15 minus 2w. There's nothing we can do there. Although I might also tack on the fact that this candidates test ready, like closed interval, also in a sense constrains us a little bit. We can no longer choose just any value from among the possibilities we had. We're going between 1 and 7 only, which is probably reasonable when it comes to making a box, honestly. Would you want a box with a width of like 0.03 inches? Like, it's like that by that, and then it's like super tall. That's weird, right? That's just uncomfortable. So here's what we got. The question for us, of course, though, is, well, what is the surface area of a rectangular box? And let's get this into your head here for a second, because I think it's easy to get thrown off by this. But basically, the surface area for a rectangular box is going to be the sum of the areas of all 6 rectangles on the outside. And if you're like, wait, are there 6 sides? Just picture a 6-sided dice, right? It's basically 1, 2, 3, 4, 5, 6. So for us, though, those side lengths are going to vary a little bit. It depends on which sides we're looking at. So I'm going to do a quick inventory of what those sides can be. First, I'm going to point out that the base is going to have area W squared. There are 2 of those bases, one on top, one on the bottom. So in my formula, I'm going to have 2W squared. Again, I'm sort of geometrying this out of nowhere to get this thing started, by the way. For the other sides, all 4 rectangles are exactly the same, because all of them are going to be a width for the base and a height for the length, basically. So for those other ones, there are 4 individual identical rectangles that form the outsides, the lateral surface area of this, what do we call it, box. And each one of those is going to be W times 15 minus 2W. And you'll notice, by the way, that I'm just sort of like dropping the pretense of putting an H in there and then substituting 15 minus 2W in. In a sense, I think we've done that enough for you to get the feeling that, like, yeah, that's where that's going to go. So this is going to be our surface area formula. And I'm just going to put over here S equals that. Like, basically my stomach's rumbling a little bit. There's still football on today. I'd love to go back and watch more of it, especially because, where can I knock on wood? My fantasy team is way ahead right now. Go figure. I was way ahead last week, though, and I lost because of the Dallas Cowboys defense. So, live and learn. Like I said, fingers crossed. But for us, we have everything that we want here. So for my S, I need to get this to be just kind of clearer and easier to differentiate. So I'm going to go ahead and do some quick moves here. This is just algebraic maneuvering. It's 4 times 15W minus 2W squared. And if I distribute that 4 in, I'm seeing S is 2W squared plus 60W minus 8W squared. And gee, that's going to be kind of awkward looking, but that's okay. 60W minus 6W squared. So, okay, fair enough. There's our surface area formula as a function of the width, which makes sense. Everything was defined as a function of the width. It's all good. We can work with that. From here, I'm going to calculate the derivative. So S prime of W, effectively. It's going to be 60 minus 12W. And effectively, we want to know the critical numbers. It's going to occur at 0. So that's going to give us, it looks like W equals 5. So interestingly enough, W equals 5 has also come up in this particular problem. Just sort of interesting, but it's cool. We can go with it. I did, by the way, last time a sign chart to do this. But if you think about it, because this is a candidates test problem, we don't need to check if this is a max or a min at all. All that matters is that it's critical. We're going to use this information alongside what we have up here with our endpoints. So basically we have those endpoints up there at x equal, sorry, not x, what do I think this is? W and 7 to create a candidates test table and actually check which one produces the largest surface area and, which one produces the smallest surface area. Although we will actually find which one produces the largest surface area as well, based on what the information we have, based on the interval we're given. So, okay, let's do it. Let's set up that table. So we're going to look at W. Hope I'm recording. Good, it says I'm recording. I'm still getting used to this. I don't know if you listened to the video earlier, but I'm recording on OBS for the first time because I had to replace my computer. And that does a great job with the sound. It cuts out the sound of the computer fans, which are really loud. But unfortunately, I don't trust it because I haven't been doing it for 7 years. Or technically, I haven't been doing it for 5 years. Okay, so I'm going to do this right this time. What is S equal to? It was right here. S was 60W minus 6W squared. And we have 3 values to plug in. We have 1, we have 7, and then we have 5. And we are looking for the smallest one. Can we find it? I hope the answer is yes. Otherwise, we got problems. So what is S of 1? It's going to be 60 minus 6 equals 54. So that's a decent surface area, but I don't know the scale of all these other answers just yet. If I plug in 5, so that's S of 5, That's going to be 60 times 5 is 300. This seems larger. Maybe I'm off here. And then 6 times 25. So if I think this through correctly, 300 minus 6 times 25. Well, 4 times 25 is 100. So add 2 more would be 150. So 300 minus 150 equals 150. Now that is a big boy compared to 54. So kind of nice. It's definitely not going to be the minimum surface area. But 7's here. Let's just make sure that 7 isn't the candidate. So that's going to be 60 times 7, which is 420. And then 6 times 49. Thanks for playing. I can do this. This will be 420 minus 6 times 50. And then I'm going to add back to that the last 6. That's sort of complicated, but effectively what I'm doing is I'm multiplying 6 times 50 minus 1. 6 times 50 minus 1 will give us 300 minus 6. And then we're subtracting in that case. So that's going to be 120. Looks like 126. And you know what? It doesn't even matter because the smallest one is right here. In fact, if I were smart, I wouldn't even bother. I'd probably just scratch this out on the AP test if it were on there, so that way we are covered. So that's my smallest one right there. So based on this, we wanted the smallest surface area. We used the candidates test to verify which one is the smallest, and that's going to do the trick for us. Based on what we just found the smallest one. So in this case, the smallest surface area. And I'm going to be lazy after all this careful plotting work here. The smallest surface area is, and we saw 54, and then it was 54, we're talking surface area, so it'll be 54 inches squared. And then although it doesn't ask it, I'm just going to say when W equals 5 inches. So that was interesting that 5-inch length, or the 5-inch width, actually did once again give us the optimal value. I don't know if optimal feels right. The value we were looking for. But hey, we did our job. So there it is. We got our minimal surface area. And quick check here to make sure I did it right. Oh yeah, 54 inches squared. I am almost done. So I think I got one more in this video. And then back to the rest of my life. So we're here in the final problem of this set of video solutions, and I took a little bit longer between, not just because I messed up when I started recording this particular section, but because I created a demonstration in Desmos, and amazingly it took me 3 minutes. I'm getting really good at those things, but the more important thing for me to note here is that I think that demonstration that I'm going to show you in here is what makes these video solutions so dynamic. Whether someone uses it or not is sort of its own question. This is the last problem on the assignment, even though this was the exact problem I chose to include on the exam in 2022. Take that for what it is, not that you're watching, but if you are. I think that the video solutions offer things that can't be offered any other way. I can't do every problem with you in class. Again, I've made the choice not to. But instead here, you're going to get the opportunity to not only see me work through the problem, but see me add to it a dynamic animation, effectively, that demonstrates graphically and visually what the maximum area actually is. It's just kind of a cool thing. I'm pretty proud of myself for coming up with it right now, especially because I am starving at this moment. And also I gave up football to make these video solutions for this week. I didn't get to watch anything in the afternoons. So that's fine. Here we go. Let's start the video with the actual solutions part. So looking in here in our situation, we have a sort of geometric problem mixed with a graphical problem, which turns out to be algebraic in nature, but also solved by calculus. It's a pretty awesome and excellent math problem for us to deal with. So what it says in this case is that we've got a rectangle inscribed in the region in quadrant 1. So our rectangle is locked into quadrant 1, meaning it's bounded by the x-axis and the y-axis in that section. And it's also bounded by the graph of 6 minus x minus 1/8 x squared. So just to kind of illustrate it here in this little picture, this is f of x, that particular quadratic, and we've got a rectangle inscribed by that graph, or inscribed in that graph, so in that tiny little section. So the idea here is that if this was a different time, I could go ahead and just sketch out different versions of that rectangle. So to be inscribed, that upper right corner is always going to be on the curve. So effectively you can tell as I draw these that depending on where I put that point in the upper right corner, we're going to get different sized area or different rectangle areas. And just imagine me putting it all the way down here. That's a tiny rectangle compared to one that's kind of more towards the middle. So in fact, in this question, or in this problem, what we're trying to figure out is which of these rectangles that we could draw, and there is an infinite number that we could draw, which one is going to provide the largest rectangle underneath that curve. And if you hear that language of under the curve and you're a person who's taken calculus before, you'll recognize that it sounds a little bit like anti-differentiation and integration, but this isn't really related to it. This is purely a geometric problem, just ported into this context. So don't get too far ahead of yourselves, although I like the way you're thinking. So in this case, as it says, we want the area of the largest rectangle, and you can assume just based on that since we're looking for areas of rectangles, we're looking for width times height, or length times width, however you want to think about it. And then basically from here, to try to figure out what the constraint is, I think it's actually more obvious than it might seem. The constraint is that our rectangle can't be any size. It's got to be limited by f of x up there. So what I'm going to do is I'm going to call this not f of x, but y. Y equals 6 minus x minus 1/2 x squared. And the reason I want to do that is because I'm going to label my rectangle in a very particular way. I don't want to call it width and height. I want to effectively call it something different. In fact, I'm going to change it right now. I'm going to call that rectangle, the dimensions of that rectangle, x and y. And the reason why I've chosen that is that this is our x coordinate. Notice that it is an x coordinate on the graph of this function. And then the height of that rectangle is y. And since y is just 6 minus x minus 1/8 x squared, effectively we can do all of that and get everything in our rectangle in terms of the values x and y, which feel natural in a problem that's based in the xy plane. So based on this, the dimensions of our rectangle, the area of our rectangle, will just be x times y, which is great. Now, I said that we could actually go through and I could demonstrate what this looks like, and I'm going to do exactly that. Basically, before I dive in and actually do the rest of the math, I think it really does help if you see what this looks like, if you see what's happening here. So effectively what I've created is I've created the graph of our function. There it is, 6 minus x minus 1/8 x squared. And then I've created a bunch of relationships here that will generate our rectangle, as well as tell us the area of each rectangle, as I change values of c at least. So notice as I move this slider for c over, the area for the rectangle is getting bigger. Like, I'm hoping you can see that. Let me do it one more time. Starts at 0 because literally at 0. It's not a rectangle, it's a line. And then as we add some c, meaning we move x further out, our area gets bigger and bigger. So these rectangles have bigger areas than the earlier ones. But we're going to reach a point at which the rectangle stops getting bigger. Oh, there's an area of 7. Oh, but it's getting bigger from there. Oops. 7. Oh, whoa, you see it. Did you see it? I saw it. 7.034, 05, and then 04. So somewhere in this ballpark right here, our rectangle gets as big as possible. Notice that after we go there, it starts decreasing once again. The area is getting smaller. So effectively, that's what we expected. But like, we're looking for some value in, let's make sure I do this right. We wanted it was like 7 point something. I'm thinking our rectangle area is somewhere in, ooh, that looks pretty big. Somewhere in this ballpark. That's going to be our largest rectangle we can possibly get. And that's exactly what our problem is trying to solve. We're going to try to figure out what x value, because that will of course determine the area of the rectangle, will produce this largest area rectangle. So that's exactly what we're going to do. We're going to actually solve this algebraically first and then use calculus to find where the maximum occurs. So let's do it. So to start with, we have that constraint, we have that objective. Let's bring this stuff together. So first and foremost, we have the constraint already established. So if we want to get a as a function of x, we're going to take that a equals x times y, and we're going to transform it instead into x times that new version of y, which is 6 minus x minus 1/8 x squared. And from here, I'm of course going to distribute the x in, and I'm going to get area as a function of the x coordinate we choose, which will be 6x minus x squared minus 1/8 x to the third. And that's a terrible looking 3. I will fix it. So from here, of course, if we want to solve this problem, we want to find critical numbers. So I'm going to differentiate this. It's going to give me 6 minus 2x minus 3/8 x squared, which, by the way, this is a great time, as great a time as any to point out that this is a calculator problem, because this could be fairly complicated for us to go through. I will have to use Desmos to find this because I still don't have a graphing calculator thing on this computer. And then, of course, we have to solve and find this where this is equal to 0. And I will say, by the way, that you could do this problem by hand. In fact, I have my solutions for this one pulled up already. And I do actually solve it. I think the solution turns out to be -8 plus 4 root 13 over 6. But yeah, let's not do that. Let's just find the 0 on the graphing calculator. Like, why go to that mess? So in this case, by the way, it should be noted that the only x values that we can potentially use here in order to be in this region will be between 0 and 4. So in fact, you could also say that there is a baked-in constraint here between 0 and 4. But let's just go check what this turns out to be and go from there. So we need 6 minus 2x minus 3/8 x squared, which, by the way, we have f of x, so let's just put in f prime of x. We'll take advantage of Desmos in this case. Oops, semicolon I don't think has a mathematical knowledge or term. So when we put that in, if I'm doing that correctly, was it 6 minus x? It was. Okay. Did I accidentally miscalculate that? Let's see here. Oh, it wasn't. Yeah, sorry. We want 6 minus 2x minus... Yeah. There's a mistake here. I can't choose just f prime of x. Of course not, because that doesn't include the relationship that we have. So instead, let's just call this a of x. And a of x is going to be equal to, it was this times x, so I think it was 6 minus 2x minus 3/8 x squared. And, oh, look at, so interesting, kind of cool, isn't it? It looks really close to the corner of that rectangle because we were really close to like numerically estimating the maximal area. That's actually really neat now that I think about it. I'm just going to clear it out so we can see it. So our only critical number is right there. It looks like 2.141. I have more decimals here, so I'm just going to go ahead and include them really fast. But there's our value. So where is the critical number? It gives us x equals 2.14, and it says 0.735. I bring all this up because it should be a, you should make it a habit to not change or not round before your last answer. It's only the final answer that you round. You're not supposed to round what are called intermediate values. So what I'm going to call this is I'm going to call this C for the critical number. I'm just going to give it that name. Had I my graphing calculator, I would actually store it as alpha C so that I could use it for that way. That way I keep full decimal integrity as we go through. Those words don't mean much for you. I just mean don't round anything until the very end. There's your recommendation. So with that in place, this is really cool. We've got our value for this. This is supposedly going to be the x value that produces our stuff. So we'll get there in just a second. But of course, it also says we're supposed to verify that this is our answer with the second derivative test. So I'm going to do that first. I just prefer to get that out of the way. I want to make sure that I have a maximum basically before I go forward, even though we've already shown visually that it is going to be a maximum. So with the second derivative test, I'm going to compute a double prime of x first. That's going to be negative 2 minus 6 over 8 times x. And by the way, to calculate this at specifically x equals c, I don't think we actually have to do anything fancy here. We don't need to actually find the value. A double prime of c is going to be negative 2 minus 6 over 8 times something positive, and that is most definitely going to be negative. So basically the second derivative at our critical number, which was a positive number, will be negative 2 minus something, which will of course be negative. Therefore, we can state that a is concave down at critical number c, which means that we have a local maximum. And of course, if you're wondering why I'm saying local as opposed to global, this is actually the global maximum as well. It's just 0 and 4 don't necessarily make sense as values because they would imply that our rectangle has no width or no height. So I'm just going to call it a local maximum in this case just to be safe. Like technically that is a local maximum. We're on an open interval basically. That's creepy. Why is my printer making noise right now? That's not nice. Okay, if something prints out and it's creepy, I'm showing it on here and I'm including it in the video. Let's just be clear about that. I'm not going to suffer being haunted in silence here. What I am going to do, though, is I'm going to finish this problem out. So A is concave down at that point, so we have a local maximum. So our last thing is to actually find what that largest area, rectangle area is. So to do that, we're going to plug in C. We're going to get A of C is equal to, and it looks like we're going to have C times 6 minus C minus 1/8 of c squared. Again, that c value is from right here. It's what your graphing calculator would come out with. And at this point, I am going to pull this out. Oh, interestingly enough, our answer does match what I got on when I was just pulling it up on Desmos. So this is going to be approximately equal to 7.035. And then there are no units here, but I noticed in my solutions I included units squared. So I'm going to go ahead and do that just for the sake of completion and being parallel there. But there is our stuff. And like I said before, this is kind of cool. Like if we go up here and actually work it out and move C over, I mean, right when it gets to that point, like that is our maximum area. And our area down here, it says, is 7.035357, which is cool. Like we're verifying what we saw on here. There is more or less our maximum area. Now, why does it say our area is not... Why is our area not showing up there all of a sudden? That's frustrating. Is it because that variable's there? Oh, that's why. Okay, cool. Let me just call it a different name then. B. There. B still. And so there we go. So cool stuff. Like you got to see some excellent like demonstrations to go along with it. But more importantly, I worked through this problem. And like I said, I included this exact model question, the inscribed rectangle optimization question on last year's exam for this unit. And I feel like it's a great candidate. Candidates test. I feel like it's a great candidate to include again. I just think it's nice and concrete. I can make the numbers come out cleaner, or I can make it a calculator problem. Lots of really good options to go with. And there's some really cool things for me to look for in your work that allow me to kind of assess points really nicely. So, I'm not going to promise it, but I feel pretty good about this being a good candidate possibly to use. So, in any event, though, I am finished with these video solutions. And this was, I don't know if anyone caught at the very beginning, this is the last set of Calculus AB video solutions for any lesson in the AP Calculus AB curriculum. So this completes a project that began in, I want to say, June 2019. I didn't know this one was missing, or else I would have done it before that at this point. But I think you got some really good stuff. And again, I didn't get paid for any of the Calculus AB video solutions. Those ones I just kind of did out of like obligation and interest and wanting to try it out. So all of this stuff, which is eaten up, I don't even know how many hours. What are there? There are 56 or 57 different sets of solutions. Shoot, if each one's like an hour and a half, just imagine how many hours of my life have been spent doing this. I'm not going to imagine that. I'm just going to stop and go back and make myself dinner. So yeah, thanks for watching. Hopefully you got some good learning out of all this, and hopefully you appreciate some of the stuff that you have here. Yeah, so thanks for watching however many of these videos or however many problems you've used. Have a great rest of your day.